Hello everyone. Hi Rohi.
Hello.
Hi Sarang.
Hello.
I don't think anyone else is joining, so let's not waste time. Let's start. If anyone else joins, then we anyways will have the recording, right? So yeah, so continuing from where we had stopped on the last day, I hope you are able to see my screen and you are able to hear me clearly also. So what we said is that we would like to do a standard scaling of the data. Now, we need to understand why we are saying that or why we are interested to do standard scaling, because we have done this earlier, right? We have already done standard scaling earlier, and we know the problems that we have faced in the linear regression use case. I'm not going to call it problems, but then it was something like it did not help, right? It did not help in doing anything, right? So uh, why are we again trying to do the same thing now? We quickly talked about this in the last session, but since it has been quite some time, so I would just like to repeat it quickly. So the reason why we are doing scaling is because what we are trying to find out, okay, what we're trying to find out is the distance. Now, before I explain this, or before we really do this exercise, there is a certain textual or there's a certain conceptual thing that we need to understand, for which I'm going to take my pen and I'm going to draw 2 points once more. So I'm going to draw these points which are in orangish color, and let's say I have 5 points which are in orange color, which are the positive points. So let's say I have a data set of cancer patients, or I have a data set of customers who have churned from my company, and this orange cross means positive results, or the customers who are my loyal customers, right? They have not churned, or they have churned. So let's say the orange one represents the positive, right? So let's consider that they have actually churned, and this violet one represents the one who are the negative, which means they have not churned, right? So this is like not churned users, and the orange one, the one that we draw earlier, are the ones which have churned. So let's say we have a data set which has only 10 points. Okay, so 5 users are here, and let's say the rest 5 users who have not churned is over here, right? Now please pay attention here. Okay, what we are going to see is a very important concept when it comes to logistic regression. There will be other cases, there may be other cases also where we might find similar kind of problem. This is too early to discuss about other cases. That's why I'm specifically not going to talk about any other algorithm or any other problem, right? But in this case, what we are trying to do, we are trying to figure out the best decision line, right? That's what is our objective. Okay, let's try to be very clear on that. What I have are two sets of points, 0 and 1, and I know that I can fit the points using a sigmoid function which looks like this, but that's not my objective. My objective is this. I have to find the decision boundary, right? My objective is the decision boundary. What is the output of the model? The output of the model is this. Output of the model is my sigmoid function, but my objective is this. Objective is to find the decision surface. Now, always it is not good to have a decision boundary divided at 0.5, right? 0.5 is under the assumption that you have very good and very well clarified, let's say, data. Now, obviously, in this example that we are seeing over here, right? In this example, the data set, the points that I have taken, they are already clearly bifurcated, so there is no issue, right? They are already clearly bifurcated. So I have good amount of segregation between the orange points and the violet points. So there is no issue here. So maybe I could have lived with a decision boundary of 0.5 also, but the objective, okay, the mathematical objective is to find a decision boundary, okay, which maximizes, okay, essentially it maximizes the distance, okay, from the 1 points to the decision surface and from the 0 points to the decision surface. So a line, as we have already talked about in earlier sessions also, is called the best logistic regression finding or the best decision surface, where, right, where the distance from that surface or from that line to each and every set of points is actually maximum, right? Obviously, if I take another example, just to quickly recap, if I take another example of a line which is something like this, then my light colored orange line, so this line over here, let me take another color, let's say blue. So this line over here, let's say this is L1, and this black line over here is L2. L1 is actually not so good as L2 because L2 has a very good distance from all the points. L1 is quite close to this point and quite close to this point, right? So there is an error, or there is uh, a chance of doing a misclassification quite easily. But if I have a line which is L2, if I have a line which is something like L2 where the distance is really good, right? The distance is really far, then that is better than a line than L1, right? So mathematically, I can say that this is an optimization problem. This kind of problems are also known as optimization problems, where we are trying to figure out the best decision surface, or we have to determine the best decision surface where I can draw this hyperplane or this line which is going to maximize, okay, which is going to maximize what? My distance, right? So if I am going to mathematically write the distance, and this is something that I would like you to read about, this is part of linear algebra, this is also part of vector algebra. So if I have a line which is something like this line is obviously denoted by an equation which is y equal to mx plus c, right? Obviously this line is denoted by y equal to mx plus c, right? Because it is a linear line, it is a straight line. Now I will assume for this time being that c is equal to 0, which means the line is passing through origin. So only to make the equation, only to make my life easy, I'm just going to consider c is equal to 0, which makes y is equal to mx. Now this mx can also be written as, w transpose x. Mx can also be written as w transpose x, where w, okay, this w represents the weights, okay, the weights of each and every x, and x represents my features. Okay, so x are my features, x are my feature columns c1, c2, c3 until cn. Let's say I have n features which are there in the data, and my target is obviously 1 or 0, and w are the weights, right? And we have already said that w are the weights that we are going to find out. So basically this function, right, this s curve which is coming out of the logistic regression, this is ultimately going to find my value of w. So if I put this in a mathematical terminology, if I put this, let's say I'll do control Z 2 times. So if I put the mathematical terminology behind this sigmoid function, right, then it comes out to be this, right? The mathematical terminology in terms of linear algebra is going to be this. Okay. Now, why are we taking a transpose? Because that is the very simple concept of matrix algebra that I would like this expression, right? This expression has to expand to w0 x0. I have considered x0 to be equal to 1, so hence I get or let's say w1 x1. So this is wrong. I'm sorry, friends, this is wrong. W x or m of x can be expanded as w1 x1 plus w2 x2, right? Until wn xn, right? So what this means, if I convert this equation, if I convert this equation into matrix formula or into matrix format, then I clearly see that I can represent, okay, I can represent the w as a transposed vector, which then is multiplied, by an m cross n vector, okay, or an m cross n matrix. So w is, let's say, a c vector, or it has only one column and a c number of rows, right? So this will not be c, actually. Let me just remove this. So the number of rows in W will be equal to n actually. So the number of features which we have is also equal to the number of W's, the number of weights we are going to have as part of the output of the model. So W is going to be a vector, a 1D vector of n rows, and I have the features matrix which is m cross n. So m is the number of rows of features which I have. Let's say in this data set we have something like 7,000 rows, right? So in our case m is going to be 7,000, and let's say in this case we have how many, 29 or 30 variables, right? So if I have feature variables which is like 30 features, so n becomes 30, this n becomes 30, m becomes 7,000, right? So mathematically, or in terms of linear algebra, this is how it can be represented, because then I can easily multiply things. If you try to remember the basics of matrix algebra that we have already studied, then what we do in case we multiply this, right, then this multiplication, this output becomes this, because the multiplication of a vector with a matrix is going to be w1 multiplied by x1 plus w2 multiplied by x2 plus w3 multiplied by x3, and so on and so forth. So clearly in this case, this representation actually is wrong. I shouldn't have represented it like this. uh, the representation would have been each and every row is each and every x entry. So x1, x2, x3, and so forth, right? So that comes out to be this equation, which I want to find out, which I know that this is going to be the equation because I have a straight line, which is fine, right? Now my point is, what is my objective then? My objective is to maximize the distance from, or the distance from the hyperplane, or my best line, or my best decision line from each and every data point which I have. If that is the case, then I have to maximize the value of this. I have to maximize the value of this. If I maximize the value of this, or the errors which are caused by this, then my job is done. If I'm able to maximize the values of the errors which is caused by this, right, then I'm done, right? Why? Because if I maximize the distance, okay, which can be represented something like this. Let me take another pen. So it can be represented like sum of I equal to 1 to n w transpose of xi, right? So if I am trying to maximize this, clearly I can do this as w transpose I also. So if I'm trying to maximize this, then I get this line, okay? Then I get one of the best lines, which is really possible, which is really the best decision boundary, right? Now keeping this in mind, what I'm going to do, I'm going to clear all the drawings now, okay? And I'm going to show you a very funny scenario, and that funny scenario is going to tell you why, okay, why we need to do the feature scaling, right? That principle is also known as squashing. So in some books, in some PDFs, you will find that principle being called as squashing. So again, I'll go back to our original example. Let's cut down all the math. You don't really need to know all the math. You just need to know what is the background of that math, because you will find that math from time to time, okay, in variety of different books, in variety of different text which you are going to follow. So again, going back to my age old example, this color represents 0, and this color, this orange color, represents 1. Actually this is a red kind of a color, I don't know. Okay, so now my intention is to find a decision boundary, right? So let's say I have written my algorithm. Obviously, you can try and visualize this. This algorithm will be iterative in nature, right? This algorithm is definitely going to be iterative in nature. Why? Because I have to find the lines, right? I have to find the lines, and then I will select the best line. So maybe I have found a line which is, let's say, something like this. I found a line which is something like this. I found a line which is something like this. I found a line which is something like this. Then out of all these lines that I have found, right, then I select the best line, right? Then I have to select the best line, right? The line where I have maximized the line's distance from each and every point, right? That's exactly what I'm going to do, right? That is exactly what I'm going to do. And by the way, just to clarify, not to confuse you, if these are, oh, sorry, if these are the points that I have, let's say these are my positive points and these are my negative points, and if I find a decision boundary which is something like this, I have this W, which is actually the normal on top of this line. So if this line is represented as pi, or this line is given as pi, then this becomes my w, the same w which I was using in my equation, right? So this w is in certain kind of a direction. In at least one direction, this w will be. So let's for the sake of this discussion, let's say that it is towards this point. Am I there? Yeah. No, okay. I hope you are able to see me clearly. Yeah. Or you are able to see the screen, right?
Yes.
Yeah. Okay. So uh, l- this w will be, since it is a vector, it has a magnitude and a direction, right? So that is the basics of a vector. So it has a magnitude and a direction. So let's assume that it is directed towards these x points, which are on this side, right? On this side. So these x points are, let's say, the positive points, right? And these x points are my negative classes, right? Now what I'm trying to do, I'm trying to create this line, find this line pi, which has the best distance from these x points, right? Now keeping this in mind, what I'm going to do, I'm going to draw one line. Let's say I have found one line. Okay, I found one line, which is this line. Okay, and I have found one. I can clearly see intuitively also. I can clearly see. I don't have to do any mathematics. I can clearly see this is a very good line. This is a very good line intuitively. But let's say, okay, let's say if I do a mathematics, if I try to take the distance of each and every point projected on this line, okay, just like this w, okay, this w being a perpendicular, so I can draw the perpendiculars. I can draw the perpendiculars. This becomes the w's, right? So on this side the w's are going to be positive, on this side the w's are going to be negative. So I'm going to take an absolute value, okay, so that I get the distance. Now let's say these values over here, these values over here, these distances over here, let's assume is equal to 1, and the distances on the negative side, on the or on the side of the negative points, they are also equal to 1. So my line is so good. Okay, so what I'm trying to say here is my decision line is so good. I found one of the best decision lines where it is exactly and equally distant from each and every data point, irrespective of whether that data point was a 1 or a 0. Right? So obviously, this is my best line. Right now, I am really happy. I have a very good model. I will go with full confidence. Okay, I will go with full confidence in front of my client, and I'm going to say that, sir, I have done an exemplary job. I am so proud of myself. Now, see what is going to be the problem. Now, let us introduce a problem. Life is full of problems, right? So let's introduce a problem. Okay, the problem that I'm going to introduce now, and for that, unfortunately, I'll have to clear all the drawings. I did a mistake. I have to clear all the drawings, and let me draw those lines once more. 1, 2, 3, 4, 5. Okay, these are my positive points, and these are my negative points. 1, 2, 3, 4, 5. Now, instead of that, let's say I have not 10 points but 11 points. I can have a data which is not entirely balanced, right? In real life we will not find any data which is entirely balanced. So let's say, just for the sake of this assumption or this discussion, let's say I have a negative point which is somewhere here. Can you see the point? It is just on top of the widgets field, right? So I've just drawn this point over here. So this is a negative point, this is a negative class, right? And we already know this color represents a positive class. So I have 5 positive points, right? And I have 6 negative points. So total I have 11 points. Now what do you think the model is going to result? Let's say I run the model and the model comes up. Okay, the model comes up with a line which is something like this, right? Let's say the model is going to come up with a line which is something like this, right? And it is trying to find the distances. Now obviously this line over here that I have iteratively found is intuitionally very bad. Okay, intuitionally this line is really very bad, right? But let's try to see what is happening over here. Let me control Z that, or I have actually removed this point. Let's go back to our previous example where we had 10 points. What was the distance from each and every point? 1, right? The distance was 1. I had a line here, right? I had a line which was something like this. I had a line here, right? And the distance on the line, projected on the line, was equal to 1. How many points I have? I have 10 points, right? How many points I have? I have 10 points. Let's say in that scenario also, I had this outlier. And let's say, just for the sake of the discussion, let's say this distance is 90. Okay, let's say this distance from this hyperplane to this negative point, which should have been on the other side, but as per my data, this point is here. So let's say this distance is 90 and the rest, all of the distances are 1. So I have a total distance, okay, total distance of all these points is equal to 1 plus 1 plus 1 plus 1 plus 1. These 5 ones are for the positive points. Maybe what I can do, I can remove this and I will take the actual color to draw the line. So that will be easy. So 1 plus 1 plus 1 plus 1 plus 1. So 5 times 1 because of these 5 points. These 5 points have a 1 distance from the line. And then I again have these 5 points which have negative 1 distance. So minus 1, minus 1, minus 1, minus 1, minus 1. True. Now this is equal to 90. So this is on the positive side, right? This is on the positive side, but the value is actually a negative value. So my line is going to consider the value to be negative, right? This value will be considered as minus 90. Why it will be considered minus 90? Because it is a violet point. It is a negative point. So that's why I'm going to consider this as minus 90. I'm simply giving it a sign. I hope you got the point here, right? I'm giving plus sign to my plus points. I'm giving minus sign to my minus points. Or to be specific, I am giving minus sign to the distance from the hyperplane to my negative points, right? Because they are negative. And I'm giving a plus sign to my plus points as the distance from the hyperplane, right? So taking that, what is going to be the output of this? This will be minus 90. Right? Output of this calculation will be equal to minus 90, right? What happens now? What happens now if my decision boundary was somewhere here? If my decision boundary is somewhere over here, then what is going to be the case? Let's try to imagine that this distance over here, right? This distance over here is let's say this distance over here is 5, right? And I'm going to consider a minus 5 because it is a minus point. And this distances are 1, 2, 3, 4, and 5. Right? So each of the positive points are one slider or one pointer away from the hyperplane. Right? So if I take a total, what will be the case? 1 plus 2 plus 3 plus 4 plus 5. Right? 1 plus 2 plus 3 plus 4 plus 5. And then I have this. Okay, these points. These are also, let's say 1, 2, 3, 4, 5. So minus 1, minus 2, minus 3, minus 4, and minus 5. I hope you got my point, right? So this distance is also considered as 1. This is considered as 2. This one considered as 3. This one is considered as 4. This one is considered as 5. So these two distances cancel out. What remains is minus 5, right? What remains is minus 5. Now I told you, right? I have already told you earlier, right, when I drew this diagram, that I can have points here and I can have points here, and in only one direction my W will be pointed. So I have to take what, right? I have to take what? I have to take uh, the the pluses and the minuses in the right way. But while I'm doing the calculation, my point is to first of all find the maximum value, right? I used to do that in case of, let's say, sum of squares, when I used to do, or the mean sum of square, or the root mean sum of square, where I used to take the absolute value irrespective of the sign. But in this case, I have to take the sign. I have to consider the sign because that sign is going to tell me how many correctly classified points I have, as opposed to how many
correctly negative points I have, or let's say I have a point which is over here, or it is classified here, or I have a decision boundary which is this, and I have a negative point which is this 0, and I have a positive point which is this 0. So there are two misclassified points in this case. The rest 4 points are classified entirely correctly. So whatever is on the positive side or this side in the same direction of the W line, if they are all positively classified, then I can confidently say I have a model which has done a very good job, right? But obviously, from the outcome itself, I'm going to find out what is going to be or how many points are there, which we are going to code also. So we are going to code and find out how many true positive or true negatives or false positives and false negatives are there, which is going to indicate how many misclassifications I have done, right? So basis the misclassifications also, we are going to determine how good or how bad the model, but we have not reached that stage. You have to first of all find out the best hyperplane, and the best hyperplane is what? Which maximizes the value, right? We have already defined it, which maximizes the value. Now friends, let's come back to this problem. What is happening here? Which line is better as per math? Is it minus 90 or is it minus 5? Because mathematically minus 5 is greater than minus 90, right? Which means mathematically this blue line is actually better than the black line. Is that really the case? The answer is no. This black line misclassified only 1 point, and this blue line has misclassified 10 points. Even after that, the blue line has a weightage of minus 5, the black line has a weightage of minus 90, right? Now, why did this black line had a weightage of minus 90? Because of this distance. This distance was minus 90. The negative point was at a distance of minus 90. That's why this calculation came out to be minus 90. True. If I am able to do something to take care of this distance, then most probably this line can be converted into a better line or a better model. What do? I do scaling of the data. Why do I do scaling of the data? Because it is quite clear that this point over here is an outlier. All the negative points are lying over here, and this lone guy is at the top of the mountain, right? If I scale the data points, the probability of this kind of unfortunate event happening, that the bad line got selected as opposed to the good line, is going to reduce. The chances of a bad line getting selected gets reduced. This technique, right? This technique of doing the squashing, or otherwise in the mathematical terminology, what we are going to do, rather than taking a maximum, we are going to take an argmax. Okay, we are going to take an argmax. I would strongly recommend you to read about what is argmax. Okay, argmax is just a technique that we are going to use over here, and by means of that, what we are doing is we are simply trying to, after we scale the data, we are simply trying to squash the data. How are we trying to squash the data? We already have the answer to that question. We already have the answer to that question. We know how we are going to squash the data. If the value if the value is going beyond a certain range, let's say all the distances over here were within the range of 1. Okay, so if the distance is going beyond a range of 1, or the distance is going beyond the range of 5, okay, then rather than this graph increasing like this, we squash the line, right? We squash the line. The same thing I do, for the negative points. If the negative points are going beyond a certain extent, let's say minus 5, I squash it, and hence the line which I get is exactly matching, or the structure of the line is exactly matching with my sigmoid function, right? So this is the technique which is known as squashing. This is squashing of the points by means of which we arrive at my S curve. And one of the most mathematical ways of doing this is to take care of all the outliers by means of doing feature scaling. Now, always feature scaling will not help in removing the outliers. There are certain very, very specific edge cases where a feature scaling does not really result into a positive thing. But most often than not, if I scale my data, this kind of a problem will be reduced, and it will help me to squash the points like this. right? It is going to help me limit my data points within the range. That's exactly what we are doing in case of scaling, right? We're trying to limit our data within a plus value and a minus value, right? I hope it was clear to you. If you have any doubts, please let me know, and then we can continue with the practicals.
No, Mohammed, not Mohammed.
No doubts.
Okay, and then I will let's say continue. So what we have done is we have taken these features in the last session, and we have taken these features and we have scaled them by creating a scalar object, which is a standard scalar object. The reason why we have taken them is because these are the continuous variables. See, these are the continuous variables. We already have 1 or 0 representation, or 1, 2, or 3 representation kind of thing for the rest of the categorical variables. Right? We have already dummy encoded them and so on. So I don't need to think about the rest of the variables, right? What I need to think about is these 3 variables that I have already scaled. Now, one thing that we quickly touched in the last session also, why did we do this for the training data only? Because we could have done this for the testing data also. You can do this for the entire data set also. Please don't scale the outcome variable. It is a suggestion. This can be taken as a quiz. You can try to find out why we should not scale the output variable, right? Try to find the answer in Stack Overflow. There are a lot of good answers there, or you can try to find the answer in stats exchange dot Stack Overflow, right? So you can try to find the answers there, and maybe in the next class you can share your views why we should not be scaling the targets. We should only be scaling the features, right? Now that we have scaled this, let's go ahead and let's try to look at what we have now as an output. So maybe we can try to do extrain dot head. This should work. If I do a extrain dot head, you see I have already scaled the data, and maybe most probably I can do a describe on extrain as well, and I will be able to get to how I have scaled the data. You see the mean is almost equal to 0. It is very very less value. So I have standard scaled it. I have actually normalized it, so my mean has gone very close to 0. My standard deviation has become 1, right? So that was the objective that I have achieved. So after I have done the scaling, right, of these 3 features, but I have finally achieved a mean of 0, standard deviation of 1. So that's the normal distribution rule, right? We already know in a normal distribution we have a mean which is closer to 0 and a standard deviation which is closer to 1, right? Now that we have normalized the data, right, let's go ahead and try to see one very important thing which we have not done earlier. Now, this is really going to be frustrating, right? I have tried this earlier, that's why I know, but I'm not going to spill the beans now. So let's try to look at something which is the a correlation. So what I'm going to do, I'm going to take a correlation matrix using telecom.corr. So the first problem we have is we have a lot of variables, right? Obviously, the diagonals are equal to 1. You know this now, right? We have already seen this at least 1 or 2 times earlier, right? So you understand how this table is calculated using the Pearson correlation coefficient and how we are getting the correlations, right? Now you can clearly see there is one example. I will take monthly charges, and I will come down. I will come down and device protection, no internet service, right? Device protection, no internet service. For device protection value being equal to no internet service, this has a negative 76 or negative 0.76 uh, correlation, and this correlation of value is also same. This correlation value is also same. This correlation value is also same. This correlation value is also same, right? These variables have a very high negative correlation value with the monthly charges. Okay, they have a very high negative correlation values with the monthly charges. Now we can try to plot this. I know we can try to plot this. So what we can do is that import C bond as SNS, and we can try to import this library. We can do that heat map kind of thing, and we can plot this, and we can find out. Okay, we can find out the cases where uh, we have high correlation, and we are going to remove those features from the data where we have a very high correlation, because if those features are intercorrelated with each other, the same concept, okay, the same concept which we had in linear regression works equally for logistic regression also. We have to get rid of multi-collinearity problem. Multi-collinearity should not be there. It must be handled, it must be taken care of, right? So let's try to see what we can do over here. So SNS, or maybe I'm going to do this, plt dot figure, in bracket fig size is equal to 12 comma 12, and then I'm going to say sns dot heat map, and inside this I'm going to say telecom dot core, right? And then, sorry, then I'm going to do a plt dot show, right? Okay, I've not imported matplotlib. Very good. Import matplotlib pyplot as plt. Right now, I think it should work. No, I did a mistake. Sorry, I did a mistake. I did a typo. So this will take some time, right? But it has resulted into the outcome. Now I can clearly see where I have the blacks. I have the blacks in some specific places. I have really dark things. So wherever I have dark things or very bright things, these are where I have intercorrelations. But I'm going to ignore this column churn, right? I'm going to ignore the column churn because churn is my target variable. Churn I'm not going to consider. I'm going to look at cases which are my feature variables, right? Which are my feature variables, and then I'm going to selectively find out. Okay, I'm going to selectively find out the columns, and I'm going to write the names of the columns here. I'm going to find them out. I'm going to write the names of those columns which are very, very highly correlated, and then I'm going to drop them, right? The, and I'm going to drop them. Now, where is it? You see, there is a series of blacks here. There is a series of blacks here. So, online security, no internet service. This is one such field which is always black for any other yes column. So if I have a yes column, let me take a pen, then you will understand this. So if I have a streaming TV yes, this column always has a negative correlation, as I could see over here, over here, over here, with these no columns. So online security no, online backup no, device protection no, tech support no, streaming TV no, and streaming movies no, right? So either I can remove this feature or I can remove these 6 features. But what I would strongly recommend doing is removing these features, because I could see this pattern is repeating, right? This pattern is repeating for each and every variable. So either we remove this set of features, so it will be this or this or this or this and so on. Yeah, I hope you got the point. Or I'm going to remove these. So a set of this 6 or this 5 or 6 features which I can remove. So I'll take any one set. Let's go ahead with one set, and I'm going to remove one set of those features, assuming that they have, or clearly I could see from here also that they have some negative correlation with them. So that I'm going to get rid of, and let's see if that is going to help, right? But one quick way I could have done this is, let's say I could have run this as 20 comma 10, and I could have said, you already know this, we have already tried this earlier. I could have done an annotation equal to true, uh, and a bit bigger figure size, so that it would have also shown me the exact values there, right? The exact values would have been shown. You see, the values are negative and they are the same. The values are negative, they are the same. Values are negative, they are the same, right? So there is a repetitive pattern over here. So that pattern I can get rid of. I can get rid of that pattern, and let's see if that is really going to help, right? So that thing I can remove, and let's see if that's going to help. So let me write down the column names first, okay, and then I'm going to loop. So the first thing, I think I'll go from this side, or maybe from this side. So multiple, no, I think I can do this better if I do something like this, because if I have a list of columns, right, then it becomes easy for me to drop. So no. So I have to say xtrain is equal to xtrain dot drop, right? Xtrain dot drop, and here I have to pass the list of the columns. That's the syntax. So here I am going to pass how many columns I have. 1, 2, 3. I can see 4, 5, 6. At least 7 columns I have, and I have access equal to 1. Please don't worry right now. When I write the column names, you will come to know why I am actually dropping them, right? So clearly, if they are dropped, that's going to help. Okay, so the first column I would like to do is multiple, multiple. Sorry, multiple. Where is the mouse pointer one? Lines. No, okay, this should be inside. Yeah, so let me just change my keyboard preference. Now it should work. So where is this? Yeah, so this field can be removed, and multiple lines, no phone service. Do I need to write the entire thing? Let me see. Xtrain dot columns. Okay, so multiple lines, yes, and multiple lines, no. Okay, so multiple lines, no phone service. I can take this. But why did it come like this? I could have done something earlier also by changing the column name. I could have altered the column names also, but that's fine. It's fine. Let's go ahead with this now. Later on, I will show you how to make the column names a little bit more better. Right. So I am getting rid of this one first. Multiple lines, no phone service. Why I am getting rid of this? Because it has a constant. This feature is there also with this point, right? And then I am getting rid of this online security, no internet service. Okay, so I am getting rid of online security, no internet service. So wherever I'm seeing that pattern, right, irrespective of how big or how small it is, I'm actually getting rid of it. So that repetitive pattern is what I'm trying to get rid of. What is the third? Multiple lines, online security, then online backup, no internet service. Well, there is online backup, no internet service. So basically, it's the alternate values. You see, one was here, second is here, third one is here, fourth should be this, fifth, sixth, and seventh, right? So that's what I can clearly copy from here, right? And I can put it over here, and I can simply get rid of the yes things, right? I can get rid of the yes things, then my job is done. This is easier, right? This is easier. So I'll get rid of yes. This is a very easy way to get the list of columns that I need to remove. So yes, I think this list is fine. So what I'm going to do, I will take this over here and I'm going to put it over here, right? I hope I have done the right thing, and I will delete this. I will also delete this, and obviously I have to drop it from test also. So I'm going to use similar function to drop it from test. I did a mistake over here. Just realized. I'm just going to take this and remove this and do it like this. So I hope this works. Yes, it does. Now let's look at the correlation once more. If I have done the removals correctly, many of these repetitive blacks and whites should be gone. Let's see if I have done it in the right way. Again, we still have no. Oh, I am taking telecom.
Mohammed, I think you have dropped the wrong columns, right? So
Is it?
underscore yes should be dropped, right?
Why? See, I what I did is something like this. You see this pattern here, right? This repetitive thing which we see over here. So what I did is that, right? What I did is here. Let's say this one. This one has a negative value. This one has a negative value. This has a negative. This has a negative. This is a negative. This is a negative. and in the same line this also have kind of a negative thing which is also repeating itself. So 0.17, 0.17, 0.17, 0.17, right? So what I did is I just took one set. I could have taken the other set also, right? I could have taken a set from here. For example, I could have taken this one, right? And I could have taken this one. I could have taken this one, then this one, then this one, and this one. Or even to some extent, is this one also applicable? No. So I could have taken these ones also. I could have taken this one also, right? Either I could have taken the yes fields or I could take the no fields. So I just selected one of them. So this pair is causing a problem. So that's why I took only one of them, right? But the mistake that I have done is not in the removal, it's in the code. It's in the code. I hope you got the point, right, Sarang?
Yeah, Bhamik, I mean, I got that. Okay, so now when you are saying x dot drop, so you're dropping basically the y-axis, right?
Uh,
Rows,
yes,
you're dropping
yes.
rows.
No, I'm upping the columns. I have already specified this one. This value one
Mm-hmm.
means x is equal to 1. So just a short form of writing that. X is equal to 1 means I am dropping those columns,
Okay, okay, fine,
right?
got it.
So x is equal to 1. Where did I write that? Yeah, this x is equal to 1 here means that I am actually dropping the columns, right?
Right.
All the rows are dropped, so it is not the selective rows. But then the mistake that I've done is I've brought them from the training and testing, and I am looking at the telecom heat map. So I should replace this with extreme. If I replace this with extreme, now the data looks quite good. I mean, at least comparatively, that repetitive thing is not there. Again, some repetitive thing is there. Some repetitive thing is there. Internet service no also is doing a repetitive thing. So why don't I get rid of this one also? Internet service no. Should I get rid of this one? Internet service no. No, I don't think I should get rid of this one. It has a multicollinearity problem. It has, but then it seems to be a very important column because internet service is like one of the primary things which we use in our phones, right? If I drop this column, I might lose some business value. Let's not drop that column. Any suggestions from your side? Should we drop that or should we keep it?
Bhamik, I think even if it is impacting something with the value towards one, then we should keep it because there is some
Hmm,
impact,
correct.
right?
Yeah.
So it is
I mean,
influencing some decision.
yeah, that's what I assume also, Sarang, because I think because we are talking about telecom churn, right? So
Mhm.
having internet on the phone or not, or whether I'm using an internet service or not, might be a good factor to determine if I'm going to churn or not. So that is what my understanding is, right? And
Yeah,
that's why,
Bhamik, but we are going on caption here, right? But we
yeah.
have to, if we are looking at the data,
uh,
so I mean, it's in negative, right? Most of the
yeah,
areas.
yeah.
Going by the word internet service, it's important.
Hmm.
But going by data, what we have at our hand, I think there
It
is
is not.
less correlation.
Okay. So let's keep it then. I, uh, or do you think we should drop? You can drop. Actually, that's not an issue. Okay, let's keep it and let's see how it goes. If it does not turn out into a good model, we'll come back. Right now, uh, yes, I know we have this sklearn thing from where I can import a library and I can do that. I'm not going to do that. I'm not going to do that because if I do that, then I will not be able to get the statistical report. I would like to try out a few statistical things first so that whatever I've done, whatever assumptions I've made, or to whatever features I've dropped, let's see if I've done really the right thing or not. And then I'll go ahead. So to do that, you know the answer. You both know the answer. I'm going to do import. Okay. stats models, okay, dot API as SM, right? So why I'm choosing stats models is because the model that I'm going to create using this library is going to give me a detailed output or a description or of what my model is actually doing in terms of the p values. Looking at the p values, I can come to know, I can understand whether my model is correct or not, right? So that's exactly what my intention is, right? So now I'm going to create a logistic regression model. So to create a logistic regression model, you can look at the documentation also, nothing fancy. What we are going to do, we are going to use a function which is GLM. So GLM stands for generalized regression models or generalized linear models. In this format only, okay, in this format or in this function only, we can pass the training data that we have, right? We have Y train and we have X train. And I know that we have already seen this. We have to add the constant when we are using stats models, right? We have to add the constant. If we don't add the constant, it does not work as expected, right? So we have to add the constant, which is my y is equal to mx plus c. That at c value I have to add, or the w0, the weight 0, I have to add. So I have to add a constant bias value. So my equation now is going to become y is equal to mx plus c plus some constant. So that constant I have to add. Okay, so using that, let's say logistic regression log r underscore 1. I'm going to call this log r underscore 1 is equal to sm. Sm is the alias that I've given. Sm dot glm. This is the function that I'm going to call. And what it takes as inputs, okay, what it takes as inputs is the training data. It takes 3 inputs. We are going to pass 3 inputs. So it is going to take the training data, first the y or the targets, then the x we, features, and then it is going to take the family, right? The family. Now this family variable is really very important, and I'm going to explain this. The family variable is going to consider what kind of logistic regression model or what kind of function we want, right? What kind of function we want. So we have a problem statement where we have two kind of possible outcomes, 1 or 0, right? So 1 or 0 being the possible outcomes, I'm going to consider that as my baseline or my hint to select a model which is none other than a binomial model, because I already know that in case of binomial distribution, something that we have until earlier, right? So in case of binomial distribution, we have only two possible outcomes, 1 or 0. The same way in our specific use case here also, we have two outcomes. So I'm going to put the value in this family variable as sm dot families, which is yet another set of library which contains the families or the group or the collection of all the type of distributions. Here I'm going to pass the function binomial, right? So if I call this sm dot families dot binomial, it is going to signify to my glm function that okay, I'm going to have a binomial thing, right? Now here obviously this will not be y and x, right? We have to pass the training data, so this will be y train and this should be x train, but then I have a problem. My problem is I have to add the constant. So let me add the constant, right? Sm dot the function was what? Add underscore constant. This is sometimes it is really very difficult to remember the functions. I would strongly recommend that you can use the documentation, but I do have a question. Yeah, no problem, Sarang. So maybe what we can do, we are already close to the session, right? So let us make a logical close over here. Let's quickly run this. Let's make a logical close over here. We are going to look at the output in the next class, maybe. So two questions, friends. Uh, Question number 1, why do we not scale the outcome features, right? And the second question, that we have not dropped the internet service underscore no, was that a right thing to do or not? Please think about this. We are going to discuss this in the next session also. Yeah. I think let's take a logical stop over here for today. Thank you, friends, for joining. Thank you.
Bhaumik, thanks a lot. Good
Thanks,
night.
Bhaumik. Good night.
Thank you. Good night.